finite fields. By the way, if you're wondering what the definition of a finite field is, I never officially defined this. It's just a field that has finitely many elements. So there's 3 theorems. The first theorem is one that we already talked about at the end of class last time. You might sort of be able to see why this is true, but there's one important thing that I didn't tell you. So right now I'm just going to state this as a theorem. It says, if f is a finite field, then its order is the power of a prime number. Then there exists a prime p, prime number, and a natural number n, such that the order of f is equal to p to the n. Okay, so you can never have a field with 6 elements. You can never have a field with any composite number of elements. You can only, if you have a field, the number of elements has to be a power of a prime. Theorem number 2. Theorem number 2 says, for every prime power, there is a field that has that many elements. And there's only one up to isomorphism. Okay? So let me write that down. For every prime p, and for every natural number, okay, there is a field with p to the n elements. With order of f equals p to the n. And this field is unique up to field isomorphism. So I'm going to put this field as unique up to isomorphism. This last statement is also pretty strong. And it's good to try to appreciate this because just think about groups. I mean, it's true that there's a group of every order, but there's more than one group of certain orders. There's more than one group of order 4, right? There's more than one group of many orders. But for finite fields, there's only a certain number of orders that are actually allowed. And for every one that is actually allowed, there's exactly one field up to isomorphism that has that order. And so the third theorem about finite fields. If f is a finite field, then its multiplicative group, f cross or f star, is a cyclic group. Okay? I'm going to prove that. That's useful to us for a number of reasons. So you know why the multiplicative group of a field or of an arbitrary ring, I mean the collection of invertible elements. For a field, f star is just, you take out 0. And then your operation is just, your binary operation is multiplication. Everything has an inverse, so the thing is a group with respect to multiplication, as long as you take out 0. And what this theorem is saying is it's actually a very special group, it's a cyclic group. So you can find, let me write out exactly what I mean. So, there exists a number alpha in f, not 0. That's what f star is, f not 0. Such that the collection of all powers of alpha, alpha squared, alpha cubed, out to, okay, let's see how many powers do I need. Alpha to the order of f minus 1 is equal to f minus 0. Of course, if you start with a non-zero element, you can never get 0. You can get everything else. The multiplicative group is a cyclic group. Okay? A number alpha which has this property is called a generator for the group. Let me just put on here a warning. Common misconception. Warning. Should write this in red. So warning part number 1 is not the warning part. This is the part that makes you feel like you understand something, and then the warning comes. So it is true that if P is a prime, the field with P elements. So by the way, I should have written this up here. If I'm talking about the field with n elements, n is a power over prime, I will write f sub n. And I won't use n either, I'll use q. If I'm talking about the field with q elements, I'll write f sub q with boldface f. So this means the field with p elements. By the theorem, we know that there is one and that it's unique up to isomorphism. And it is true that this is isomorphic to the field z mod pz. You know, z mod pz, it's a commutative ring. It's got no zero divisors. So it's a field. It's finite, commutative ring with no zero divisors. Finite integral domain is a field. Problem number 1 from problem sheet 1. However, if n is bigger than 1, it is not true. In fact, it's absurd. It's not true that f sub p to the n is isomorphic to z mod p to the n z. Okay? Not true. In fact, the thing on the right-hand side is not even a field because it's got zero divisors. In fact, it's not even true. That z mod p to the n z is a field. It's not even a field. Okay? Now, to confuse you even more, if you look at the multiplicative group of a field, we just said by the third theorem that it's cyclic, so it's generated by one element. So in a way, so the multiplicative group of a field with q elements, the multiplicative group as a group is group isomorphic to z mod q minus 1z. But the operation here is a multiplication, and the operation there is addition. It's a little bit confusing. I'm not going to write that down. But the additive group is different. The additive group looks like z mod p cross z mod p cross z mod p n times. I'm not going to go into the details of the points that I just mentioned. But I'm just going to go into now some exercises. And I think you have the warning there. Just don't say that don't say the field with 4 elements is z mod 4z because it's not true. So, example number 1. Let's take a look. Let's construct a field with 4 elements. Construct a field with 4 elements. 4 is 2 squared. Elements. So when I ask you to construct a field with 4 elements, 4 is 2 squared, what you want to do is you want to start with a field with 2 elements. And then you want to find an irreducible polynomial of degree 2. And then you want to adjoin one of the roots. Okay? The basic plan is the same for this problem and for the problems on your homework and whatever else you're going to be asked, which is that you're asked to construct a field with p to the n elements. You start with the field with p elements, find a degree n polynomial, which is irreducible, and you adjoin a root. Then you get a degree n extension. Okay? So let's suppose that let's suppose this polynomial is f. I'm going to elaborate on this plan a little bit. Suppose this polynomial is f of x. Suppose that the root is alpha. Remember, we know that for any field, there's always an extension where it has a root, and so we can talk about the root of the polynomial. And then, what can we say about the extension? Well, then we know that by the theorem that we had on the board last time, that f2 adjoin alpha, the degree of the extension of f2 adjoin alpha over f2, is equal to the degree of the polynomial f is equal to 2. And we know that we also have a basis, that 1 comma alpha is an f basis, is an f2 basis for the extension. Okay? So f2 adjoin alpha is exactly the set of numbers that can be written in the form a naught plus a1 times alpha. Actually, I'm gonna say this in a little more precise way. Hold on a second here. What do I exactly mean by this statement? Let me talk about what I exactly. This statement is already going to give me the conclusion that I want, that the thing has 4 elements, because there's exactly 2 choices for each of the a naught and a1. And so that's all that I'm really aiming for. But let me just try to explain what I mean by this statement. What does it mean, f2 of alpha is equal to this set? Well, in order to understand what this statement means, you need to have the theorem that we talked about last time. In fact, I think I'm going to make you a handout that has that theorem on it together with the Tower law. What I exactly mean by this statement, just so you know, is that, remember last time we said that our theorem said that f2 of alpha is isomorphic to the polynomials with coefficients in f modulo the ideal generated by the irreducible polynomial little f. And what I really mean by this statement up here is that okay, so I'm identifying the number alpha with the coset x plus the ideal generated by f. Our theorem last time told us that that's a homomorphism. I mean, that's an isomorphism of the 2 fields. So the arrow was going the other way. So what I really mean when I say that my field is equal to this set is, I mean that if you take the collection of coset representatives of the form a naught plus a1 times x plus the ideal generated by f, where a naught and a1 are elements of your field f2, that this is exactly a collection of coset representatives for the quotient ring. Okay? You need to keep that, even though that's a really confusing statement that I just made, you need to just sort of keep that in the back of your mind so that when you multiply together things in the field and the degree gets to bigger than 1, you remember that you're supposed to subtract off some multiple of the polynomial f. So the polynomial little f is what tells you how to do arithmetic when degrees get bigger than 1. Okay? Look, so we're done. Okay, there's something else I want to do with this example, and I need to keep moving here. I want to be very explicit with this example, and I want to write out the collection of all elements of the field, which won't take very long, since there's only 4 of them. And I want to find a generator for the multiplicative group. So F4, our field with 4 elements, is equal to, well, let's just think about all the different ways of choosing a naught and a1. I could choose a1 to be 0 and a naught to be 0 or 1. And I could choose a1 to be 1 and a naught to be 0 or 1. And those are the only possible choices. There's 4 elements in this field. Now, let's think about the next problem, which is to find a generator. For the multiplicative group. So by the way, the multiplicative group here is just the collection of non-zero elements in their multiplication. It's 1 alpha, 1 plus alpha. What do you want to guess is a generator? Well, there's only 3 elements here. You can't really go wrong. Just don't pick one. Just pick one of the other ones, and you're okay. So if I take alpha and I square it, so I've got alpha to the 1 power. I've got alpha squared. Alpha squared is 1 plus alpha. Oh wait, hold on a second here. Alpha squared. What was my? Oh, wait. How in the world can I tell you what alpha squared is if I didn't even tell you what the polynomial is? I have a polynomial in my mind. Sorry. Sorry about that. irreducible over F2 because it has no roots, and it's a degree 2. Okay? And so now, because as soon as I wrote down alpha squared, I was thinking, what am I going to do next? What's alpha squared? If alpha is a root of f, then alpha squared is minus alpha minus 1. But since I'm working in F2, minus 1 is the same as plus 1. Just if it was 2 elements. If it's not 0, then it's 1. So alpha squared is 1 plus alpha. Now, alpha cubed had better be, by Lagrange's or Legendre's theorem, alpha cubed had better be 1, and it certainly is. And we'll just do the computation to verify that. If I take alpha times 1 plus alpha, I get exactly alpha plus alpha squared. And alpha plus alpha squared is equal to minus 1, which is the same as 1 in F2. Okay? I can do another example for you, a little harder one. But before I do that, just so in case we run out of time, let me talk about the tower law. So on your homework, there's a couple. The first 2 problems are like this, where it wants you to construct finite fields of certain orders. And this is the recipe for doing it. You just find a polynomial that you know is irreducible over the base field, and you adjoin one of the roots. And then you use the theorem that we had on the board last time to understand the arithmetic and the resulting field.